Hello students, today we are going to start coordination compounds, and by the end of the video you will be able to understand the Werner's theory and some common terminologies related to it. So let us start. In coordination chemistry, we deal with coordination compounds. And what are these coordination compounds? These are the compounds composed of a metal atom or ion and one or more ligands. These ligands could be atoms, ions, or molecules that are formally donating electrons to the metal center. You can see here one of the example of coordination compound where in square bracket you can see that the central metal ion cobalt is surrounded by 6 ligands, and this is called as coordination sphere. Outside it there are 3 chloride ions called as counter ion. These amines, the ammonia NH3 is a ligand, and the electron pair available on nitrogen forms a coordinate covalent bond to the metal. It transfers its complete lone pair to the central metal ion. So basically, complex compounds or the coordination compound are the special class of compounds in which the metal atoms or ions are bound to a number of anions or neutral molecules. In modern terminology, these compounds are called as coordination compounds. Here you can see the coordination compounds where the blue ball is actually representing the central metal atom or ion surrounded by the green colored ligands. It could have the shape of octahedral if surrounded by 6 ligands, or tetrahedral or square planar if surrounded by the 4 ligands. You will be studying about it later ahead in the chapter. So, when we are talking about coordination compound, we say and we know that it consists of a complex ion and necessary counter ions. For example, you can see the structure: cobalt bonded with 5 ammonia, 1 chlorine inside the square box, and 2 chloride ions as counter ions outside it. The overall charge has to be balanced. If we remove the 2 counter ions, chloride ions, then the charge 2 plus would appear on the square bracket. The complex ion, where the cobalt will be having 3 positive charge, ammonia ligand will not have any charge, and chloride ion will again have -1 charge. So the overall charge on the square bracket is 2 plus. And the counter ions have each chloride ion have -1 charge, and 2 chloride ion thus contributes to 2 minus charge. A central metal atom bonded to a group of molecules or ions is a metal complex. If it is charged, it's a complex ion. Compounds containing complexes are coordination compounds. Here you can see that in the square box, metal complex, this is the metal complex where the chromium is the central metal ion, ammonia is the ligand, chlorine is the ligand ion, ammonia is the polar molecule ligand, chloride is the ion, and the overall square bracket is called as complex ion. Hence, a central metal atom bonded to a group of polar molecules or ions is a metal complex. If the complex bears a charge, it is a complex ion, and compounds containing complexes are called coordination compounds. A complex ion thus has a metal ion at its center with a number of other molecules or ions surrounding it called as ligands. As you can see in these four examples, it is clearly seen that the central metal ion Fe, Al, cobalt, and copper are surrounded with the ligands. Coordination entity. Metal atom or ion bonded to fixed number of ions or molecule are called as the coordination entity. For example, in this square box, cobalt is bonded with 3 chloride ligand and 3 ammonia ligand. Other examples are also here. You can see that. Hence, we have a coordination sphere in the square box. We have one ionizable anion, the counter ion. We have the central ion cobalt bonded with the ligands, and the total number of ligands is actually the coordination number. For example, here the 2 chlorine and 4 ammonia ligands forms 2 plus 4, 6 coordination number to cobalt. We have some definitions to be remembered. Coordination entity. A coordination entity. Coordination constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, hexacyanoferrate. Central atom or ion. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is called the central atom or ion. Coordination numbers. The coordination numbers of a metal ion in a complex can be defined as number of ligand donor atoms to which the metal is directly bonded. Coordination sphere. The central atom or ion and the ligands attached to it are enclosed in square brackets and is collectively termed as the coordination sphere. The ionizable groups are written outside the bracket and are called counter ions. Oxidation number of central atom. The oxidation number of central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. Homoleptic and heteroleptic complexes. Complexes in which a metal is bound to only one kind of donor groups are known as homoleptic. For example, we can say hexaamine cobalt. Here all the 6 amines are bonded with cobalt are the same. And complexes in which a metal is bound to more than one kind of donor groups, those are called as heteroleptic, where at least 2 different type of ligands would be bonded with the central metal atom or ion. Coordination polyhedron. The spatial arrangement of the ligand atoms which are directly attached to the central atom or ion defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. Let us see now double salt and coordination compounds. An aqueous solution of potassium will give the test for potassium ion, aluminium ion, and sulfate ions. Why? Because it dissociates completely into its constituent ions. On the other hand, coordination compounds are molecular compounds that retain their identity even when dissolved in water. The square bracket complex never dissociates into its ions. For example, when potassium ferrocyanide is dissolved in water, it does not give the usual tests for Fe2 positive and cyanide, indicating that FeCN6 in square box 4 negative charge does not dissociate into Fe2 positive and cyanide ions. So, on the basis of nature or addition, molecular compounds can be divided into two categories, double salts and coordination compound. Here is the difference between the double salt and coordination compound, that double salt exists only in solid state and constituent into constituent species in their solution, whereas the coordination compound retain their identity in solid as well as in solution state. In double salt, they lose their identity when dissolved. Coordination compounds do not lose their identity when dissolved. So, here are the differences. Dear students, you can do that. More salt, which is one of the very important part of your practical. The ferrous ammonium sulfate with 6 water crystallization is a double salt. Naturally existing coordinate compounds. The chlorophyll having magnesium, hemoglobin having iron, and vitamin B12 having cobalt, all are the coordinate compounds. Alfred Werner, a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their chemical and physical behavior, and finally proposed the concepts of primary valence and secondary valence for the metal ion. Let us see the history. Alfred Werner also won the Nobel Prize in 1913 for that. He developed a model of coordination complex which explains the following observations. When cobalt chloride was mixed with ammonia, 4 different types of compounds were being formed with the following formula: cobalt chloride with 6 ammonia, cobalt chloride with 5 ammonia, cobalt chloride with 4 ammonia, or cobalt chloride with 3 ammonia. And when aqueous silver nitrate was being added to them, the cobalt chloride with 6 ammonia having yellow color precipitated 3 moles of silver chloride, indicating that 3 chloride ions were present as counter ions. Similarly, cobalt chloride with 5 ammonia ion ligands precipitated 2 mole of silver chloride, indicating the presence of 2 chloride ions as counter ions, and cobalt chloride with 4 ammonia ligands precipitated 1 mole of silver chloride, indicating the presence of 1 chloride ion as the counter ion, whereas no silver chloride was being precipitated in the blue colored CuCl3 3NH3, indicating no ion was present as counter ion. The conductivity in aqueous solution also showed the same, the presence of 4, 3, 2 and 0 ions in the yellow, purple, green and blue complex of these respective formulas. It clearly showed the exact formulation of the formula, that how does the formula actually exist. So the compound 1 with 6 ammonia contained 3 chloride ions as the counter ions, and those 3 free chloride ions reacted with AgNO3 and precipitated 3 moles of AgCl. The similar thing happened with compound 2. The only thing was that 2 free chloride ions were present as the counter ions, and the final overall we could see the structures of different formulas. Measurement of the conductivity of the above complexes also suggested the same. The number of ions present in the different formulations of orange, yellow, red, purple and green compounds. Werner explained all these observations by suggesting that transition metal ions, such as the cobalt-3 positive ion, have a primary valence and a secondary valence. You can see it here, the Werner's theory of coordination chemistry. Finally, the correct formula was being calculated. The two compounds, the cobalt chloride with 6NH3 and cobalt chloride with 5NH3, have very similar formulas, but they are very different appearance because of the different chemical structures. So, coordination chemistry and coordination compounds all have this wonderful connection with each other. The main postulates are: in coordination compounds, metals show two types of linkages, primary and secondary. Dear students, remember this. This is one of the very important point in Werner's theory. The coordination compound metals show two types of linkages, primary and secondary. Primary valences are ionizable and are satisfied by negative ions. The secondary valences are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number and is fixed for a metal. The ions or groups bound by these secondary linkages to metal have characteristic spatial arrangements corresponding to different coordination numbers. Let us now revise these points in some easy form. Metal ions exhibit two kinds of valencies, primary and secondary valencies. The primary valency is the oxidation number, positive charge of the metal. And the secondary valency is the number of atoms that are directly bonded to the metal. The secondary valency is also called as the coordination number of the metal in coordination complex. So, in Werner's theory, the coordination compound metals show two types of linkages or valencies, primary and secondary. The primary valencies are ionizable and are satisfied by negative ions. For example, in FeOH whole thrice, the primary valency of iron is +3, and the secondary valencies are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valence is equal to the coordination number of metal atom or ion and is always fixed for a metal. For example, in K4FeC whole 6, secondary valence and coordination number of iron is 6 because 6 cyanide are attached to iron, and it is in a square bracket. So, Alfred Werner introduced two types of valencies finally. Primary valence, which is the oxidation number or charge, and secondary valency, which is the coordination number. Examples of primary and secondary valency you can see for this formula, where cobalt is bonded to 6 ammonia in a square bracket and 3 chloride ion as counter ions. What is the atomic composition of the complex? You can see the formula. Cobalt is bonded to 6 ligands of ammonia in a square bracket and 3 chloride ions as counter ions present outside the square bracket. What is the net charge of the complex? If we remove 3 chloride ions with 1 minus negative charge, 3 positive charge would appear on the square complex. How do we know the charge is 3 plus on the metal? Because 3 plus is required to balance the 3 chloride negative ions. Hence, the primary valence of this compound is 3, the charge on cobalt, and the secondary valence of this compound is 6, the 6 ligands. I hope you all have understood this Werner's theory and simple terminologies of the coordination compounds. Thank you.